Well, hello there, wonderful class. We're going to do, this is Chapter 9, Homework Help. Right, so let's dive right into it, because I don't have a whole bunch of time to do this. So, anytime you see heat capacity, any question about specific heat capacity, the first thing we want to think of is Q equals MCAT, MC delta T. Right, where M is the mass, C is the specific heat capacity, temperature, the change in temperature is the final temperature minus the initial, and Q is the heat. All right, so as I read through this problem, I see a lot of those variables. I got the mass, I can figure out the temperature change, and I even see C, and it's asking for the heat, so that works out well. So let's go through and write those variables out. Oops, let me do C first, stay in order. Our Q is what we're looking for. Our mass of this sample, they took a sample and it's 10.0 grams. Our specific heat capacity is 0.449, pretty close to iron, and is joules per gram degrees Celsius. And the temperature change, remember, it doesn't matter if it's Kelvin or Celsius as long as you're taking a change. So you can do T final minus T initial, which in this case it says it cools, it starts at 75, it ends up at 25.5, meaning the final, or it cools from, starts from here and ends up here. So it starts at, cools from 75, so it starts at 75 and cools it here, which is why our final, let me just write it down so it's more clear, is 25.5 degrees Celsius. And then it started at 75.5 degrees Celsius, meaning a difference of negative 49.5 degrees Celsius. Okay. Now this should make sense that it's going to be negative because it says how much heat is released. In other words, how much was let out. Right? So let's go ahead and start plugging and checking. If our Q equals MC delta T, our Q therefore will equal the mass, 10.0 grams, times the C that was given, 0.449 joules per gram degree Celsius. And then times our delta T, negative 49.5 degrees Celsius. Okay. The units of this make it so that our grams cancel, our degrees Celsius cancel, and the only thing we're left with is joules. And we should get an answer of negative 222 joules of heat, meaning another way to write that is that 222 joules was released. It's just like when you go to your bank account and you take money out, you don't say, I took out negative $25. Even though your statement will show it was negative $25, you say you took out a positive $25. That's why it's written that way. All right, then there's another question followed up that's very similar to this, and then a couple little think questions about whether things are endo or exothermic. But now we get to this one. And in these situations where you have different things, you're taking one thing and you're putting it into some other substance, be it, in this case it's water, sometimes it's something else, you're always going to think, well, actually, let's draw a picture. You're always going to think that one thing is releasing heat and the other thing is gaining heat. So we had this piece of gold, right? It's suspected of being pure gold. And you heated it up to a certain temperature. And then you put it into some water. Now, the water was initially 24, but this thing released heat and warmed up the water. And at the end, everything was 27, meaning the final temperature of the gold and the final temperature of the water was 27. Now, here, hopefully you see you have two substances or two things that you're talking about. One's the water and one's the gold. And in that situation, you have to remember that the heat that the gold released, in other words, negative Q of the gold, or this, we'll call it a substance because we don't know what it is, equals the positive Q of the water. So the heat that the gold released has to be equal to the heat that the water gained. In this situation, you're going to have two different variables. This has its own MC delta T, and this one has its own MC delta T. Eventually, we'll have negative MC delta T of the substance equaling the positive MC delta T of the water. Okay, so this would be of the substance, and this would be of the water. Remember, this negative is like a -1, So it only applies to one of these things. You're not distributing it like you would if these were adding or subtracting. These are multiplied, so you just negative to that one. Okay, so let's go see if we can put together these variables and then solve. So for our substance, our mass was 2.33 grams. Our C is what we are looking for to see if it's pure gold. And our delta T, it started at 72.4 and it ended at 27. So in other words, our delta T is 27.0 minus 72.4. And this gives me an answer of negative 45.4 degrees Celsius. All right, we'll do the same thing for our water. I'm gonna kind of run out of spots here, so let me grab some paper. Okay, for our water, we have that our mass of the water was 15.9 grams. The C of water we should have memorized, 4.184 joules per gram degrees Celsius. Remember, you need to know that. That's supposed to be a star. I don't know what that is. It's a scribble, but memorize this one. And then we have our delta T. It started at 24 degrees Celsius and it ended at 27. So our delta T is 27.0 degrees Celsius minus the 24.0 degrees Celsius. In other words, 3.0 degrees Celsius. So now that we have all these variables, we can start plugging them into this thing. So I'm gonna draw a little line down here so I have some fresh space. I like to keep everything together. So let's start with the substance, the mass of the substance. Don't forget that we have a negative sign. So negative times the mass of the substance, 15.9 grams, times the C, which we don't know. That's what we're solving for. Times our delta T, which is negative 45.4 degrees Celsius, is going to be equal to, I'm gonna have to leave some units out to save some space here, is gonna be equal to our mass of the water, which was oh, excuse me, I messed up already. This was negative 2.33. You guys are probably already yelling at me through the screen. I'm so sorry. So over here, our mass of our water, 15.9 grams, times our C, we know that's 4.184, times our delta T, 3.0. Okay. So to show you how to solve for this, let me grab my calculator. Remember, you can always put it in terms of something you don't know, but essentially we're multiplying this. It's just algebra, we're solving for x. We multiply this, we're gonna divide by that, and we're gonna divide by this. Now here you have a negative times a negative times a negative equals a positive. But even if you didn't do that, and you did it the way we're doing, and you include those negatives, you'd still get the right answer. Okay, so just to show you algebraically, we're gonna say 15.9 times 4.184 times 3, I'm gonna hit equal. I'm gonna divide it by 45.4, which cancels this out. And then I'm gonna divide it by 2.33. This gives me an answer of 1.887, and that would be joules per gram degrees Celsius. Because this had 2 sig figs, our final answer should have 2 sig figs, so our final answer should be 1.9 joules per gram degrees Celsius. It follows up with another question, and it says, is it pure gold? Well, pure gold is 0.128 joules per gram degrees Celsius. Is this the same as this? Hopefully you agree it's not, so it is not pure. Okay, moving on. So this next one here, relatively straightforward. It shows you that A plus 2B yields C plus 3D. And then over here, you'll see that you multiplied it by 3. So now we have 3A, 6B, 3C, and 9D. So essentially we took this whole thing and multiplied it by 3. If we took that whole thing and multiplied it by 3, then our delta H should also be multiplied by 3. So it'd be 120 times 3, in other words, 360 kilojoules. On our next one, we just reversed it, okay? So the C and the 3D are now over here, and the A and the 2B are on the other side. When you do that, remember your delta H sign just flips. It was negative or positive 120, now it's going to be negative 120 kilojoules. Okay. And I think from there you can do the rest, which are very similar. All right. Moving on. Okay, so it says calculate this following thing. So, you know what I'm going to do is use a whole fresh sheet of paper for this one. Okay. So, we're going to use that idea that we can flip things, multiply things, etc., and solve for this. So in this situation, we want for all of these to add up to equal this thing right here. So we want all of these to be able to add them up and equal this thing right here, but we have to manipulate them using Hess's law. So the first thing I like to do is see what I want at the end, right? I want a CH4, 4Cl2, CCl4, and a 4HCl. And then I go one by one and see if I can move things around to match this. So for example, here I have a CH4, hopefully you see it, but it's on the reactant side. Over here I have a CH4, it's the only other place for CH4, but it's on the product side. So what do I have to do? I have to flip it. Okay, so I've got to take this reaction, I'm going to flip it. And I'm going to actually write it down. So if I flip it, it would be CH4 and then yielding C plus 2H2. And then my delta H, don't forget, would now be positive 74.6. And these are all in kilojoules. Okay, let's look at the next one. Then we have 4 Cl2s. Okay, so I have Cl2 coming from here and from here, so I'm not quite sure what I do yet. Do I multiply this one by 2? Do I maybe multiply this one by 3/2? I don't know. But let's move on to the next one. It usually holds the clue. So here I have 4 HCl, but the only place I have HCl coming from is right here. Now it's on the correct side, they're both on the product side, but here I only have 2 HCl, but I need to make sure I get 4. So what that tells me is it's actually this one that I'm going to double, and this one has to stay the same, because it doesn't have anything to do with this other stuff up here. So let's first rewrite this one, where we have C plus 2Cl2, yielding CCl4, and our delta H is negative 95.7. And now this one, I can multiply all of these by 2. So now I have 2H2 plus 2Cl2, and that's going to yield 4 HCl. And then of course, what I do to one thing, I have to do to the other. So I'm going to multiply this 184.6 times 2. Okay. And that's going to give me a delta H of negative 369.2 kilojoules. Okay. Now let's make sure that all these things add up to give me this original reaction. Kind of looking at this, I see almost immediately the carbons cancel. So I can cancel anything out. I see 2 H2s cancel. And then I see these sum to 4 Cl2s, and then I have this and this left. So let's go ahead and write everything else that we have left. We have a CH4, we have 4 Cl2s, then yielding. Then we have 1 CCl4, and we have 4 HCl. Because that is, in fact, the original one that we're looking for, we know that we are good. So all we have to do to solve for the delta H is just add these up. This plus this. And when I do that, I get a negative 390.3 kilojoules as my final answer. All right. Moving on. It says enter an equation for the formation. Remember, whenever you're doing formation, this means from standard states. Remember, most things on the periodic table are monoatomic, meaning their standard state is just what they are. So, for example, the standard state of boron is just B. But some of them have, some of them are diatomics. Remember the N, O, F, Cl, Br, and I, and this is exactly how they fall in the periodic table, plus an H. These are all diatomics, meaning in nature, they exist as twos. Even though the periodic table gives the mass of just one of them, in nature, they exist as twos. So fluorine here would exist as a diatomic. All right, when we do our thing, in order to find this, we write what we're forming. We're forming BF3, but we want to make sure that it's coming from the standard states. This has to be 1. It must be 1. So you can't like double it or whatever. You're going to have to usually use fractions in order to balance it out to keep that thing to being 1. So to get a BF3, we needed boron and we needed fluorine, but don't forget fluorine's diatomic, so we got a 2 there. Boron, it's a 1-to-1, so you're good. For the fluorine though, here I have 3, here I have 2. Remember, I cannot put a 2 and a 3 there because this has to remain 1. So you always put the big number over the small number, or you could just put 1.5 if you want it, but I think the book wants you to do 3 halves because it's just more common. And that is, that's the answer that they're looking for. Now, if you go and look at the table that they provided, it shows you that the delta H of formation, they put a little circle here showing you that it happened at 298 degrees Celsius, equals negative, I think it's 1135.6 kilojoules. And that's just from this next page over here. Yeah, from this next page over here. So negative 1135.6 kilojoules. In other words, to form this, you released this much. This right here was an exothermic reaction, releasing that much energy. So you can go through and do the other ones like this. Just make sure you pay attention to where the diatomics are. All right, I think we're last but not least already. That's pretty great. Okay, so last but certainly not least, we have this one. The reason I chose this one, all the other ones, the enthalpy of formation are here. This one wasn't, so it's in your book, in your e-text, in the appendix. If you need it, let me move some stuff around so you can see this. But you can see it's in the appendix A, and if you go to appendix A2, you'll be able to find all the enthalpy of formation. So the sulfur-containing ones, this is where I got the H2S that I'll use, and this is where I got the SO2 that I'll use. So H2S is negative 20.6, SO2 is negative 296.8, but we'll talk about it here in a second. So if you ever need extra enthalpy of formations, you can Google them. That works just fine. Just make sure that they're in units of kilojoule per mole. Otherwise, yeah. Most of these are on this table right here. This one's kind of frustrating because it's not, so I want to make sure to do it. Okay, so use the standard enthalpy of formation to calculate the delta H of the reaction. I'm going to rewrite this equation just so it's a little bit bigger for me. So we have 2H2S gas plus 3O2 gas yielding 2H2O liquid plus 2SO2 gas. So again, the enthalpy of formations were from that other one. If you remember, this one was negative 20.6, so we have 2 of them. So we do 2 times negative 20.6, and that's kilojoules per mole. Remember, the units of this 2 would be moles, so the moles would cancel, and you'd be left with just kilojoules. Anything in its standard state, O2 is in its standard state, it's a diatomic, would be 0, so plus 3 times 0. So we do the reactant side and we do the product side. Water is 2 times, they actually have water here. Liquid water is right here, negative 285.8. So we do 2 times negative 285.8 plus, and then SO2, again, was not on there, but we looked it up, it was negative 296.8. Okay. So we add up stuff here, we add up stuff here, and then we're going to figure out, remember, products minus reactants. So let's add everything up. When I take 2 times this number, I get negative 571.6. And 2 times that number gives me negative 593.6. When I add this plus this, the total on this side is negative 1165.2 kilojoules. On this side over here, I've got 2 times negative 20.6, which would be negative 41.2, and the 3 times 0 would just be 0. So my total on this side is negative 41.2. Remember, our delta H is going to be products minus reactants. So everything added up on the product side minus everything on the reactant side. In other words, negative 1165.2 kilojoules minus negative 41.2 kilojoules. And when I do this, I get an answer of negative 1124 kilojoules. So the next several questions ask you something very similar to this. Again, most of those are on the table that I saw, so that should be a lot easier to handle. Always email me if you got questions, and I hope this helps. Bye, y'all.